Well, another time, good afternoon, everyone. In this moment, we start with a webinar. First, welcome to webinar Fundamentals of Petroleum Industry from Reservoir to Sales by Mr. Jorge Pinedo. Remind that they can ask their questions in the meeting chat. I am Mr. Jorge Pinedo, is a production operation manager with more 30 years technical and non-technical experience, offshore and onshore experience. His experience includes oil, gas, and unconventional fields, exploration, appraisal, production optimization, reservoir management, integrated production modeling, digitalization, project management and production modeling. Uh, HSE management systems implementations. His management experience include reservoir to sales, exploration to production, supervising both office and field person. Location work include UK North Sea, Netherlands, Pakistan, Egypt, Kuwait, Indonesia, Australia, Oman, Italy, Qatar, UAE, China, Algeria, and Peru. Jorge holds engineer offshore engineer and master engineer in petroleum engineering from Hertford University, Edinburgh, UK. So, Mr. Jorge, when you want, we can start with the webinar. Thanks, Mr. Jorge. Can you hear me?
Yes, thank you very much, Victor. Good evening and good afternoon, everyone. Thanks for your participation to this webinar on fundamentals of the petroleum industry from reservoir to sales. The agenda for today is we will talk about the life phases of a hydrocarbon field. We will talk about seismic, conventional and unconventional reservoir types, a little bit about reservoir classification, recovery mechanisms, what are unconventional resources, reservoir simulation, well construction process, which means drilling. We'll drill a well together. Well logging, completions, artificial lift, and workovers. We'll talk about the production process, downstream and refinement processes. And finally, we'll talk a little bit about petroleum products and its customers. Can you hear me okay, Victor?
Yes, Mr. Jorge. Can you start?
Okay, so we'll start with the life phases. So in the life phases, what is important to know is how a field moves from resource to reserve and then to production. So here we can see three different phases. First one is exploration, then appraisal, then development and production. What's important to note is that it doesn't matter how much gas we think oil and gas company have or oil. At the beginning, if this has not been proven or declared commercial to be recovered, on the exploration phase, basically this is called resource. So an oil and gas company could have a big acreage, but if they have not done any work in trying to determine a reserve, then it's only a resource. Very important to know, okay? At the beginning, it's called a prospective resource because only some geological reviews have been done. Then doing a bit of seismic, which we'll talk about, some core holes, and a bit of more geological review work, you could move from being prospective to contingent, but it's still a resource. Important to know, not a reserve. Then as we do more work in the final part of the exploration, we could call it possible reserves. And then as we move along in the life of the field, we do some pilot wells, we do some well testing or extended well testing, and then we can talk about probable, and then finally drilling more development wells. We have proof reserves. Why is the definition of reserves important? because when we talk about reserves, it's a volume of gas which we can produce economically, in which there is a market for that oil and gas, in which there are no environmental permit issues that will stop the development of the field. Reserves is like the gold in a bank. Reserves is what an oil company has in order to seek investment from investor capital to be able to develop a field. Okay, without having declared reserves, oil and gas company doesn't really have any value. When a company buys another one, they don't buy it because they have a good engineering team. They don't buy it because they have a nice office. They don't buy it because they have nice facilities or even wells sometimes. They buy it because of what reserves declared by the right authorities, with our certification people, declare it as reserves. So very important to know, reserves is really the key. Otherwise, it's just a resource that is only of basically no value until it's confirmed that it's a reserve. Okay, let's talk about seismic. So what is actually seismic? Seismic is basically the process by which we send some sound waves down to the strata, and as it crosses the different densities of rocks, then it bounces, and essentially it gets recorded by a very sensitive microphone, which we call geophone. But really, when you see a map like that in seismic, this is really a map of time, of how long it takes for the sound waves to come back. From here, very experienced and knowledgeable personnel called geophysicists analyze this data and try to estimate geologically what occurs, okay? But unless you drill a well, it's very hard to determine whether there is oil, gas, how much it will produce, etc. But it's the first part which tells us what geological features lie behind. To do seismic on the road, on land, you could do trucks, seismic trucks like this one that vibrate and send the waves. Offshore, you can use boats with all the sensors. And for example, in this case, in the jungle, then you need to basically use other methods accordingly. Now we'll talk about conventional and unconventional reservoirs. So where do we find hydrocarbons? On the conventional side, we find them in accumulations with sufficient volume in sandstones, which are, as we will talk later, reservoirs that have good porosity and permeability to accumulate the volumes. But also, we have other types of unconventional, like coal bed methane or coal seam gas, as it's called in other places. Tight gas or tight sands. We have shale. Shale is basically a source rock which does not have any porosity or permeability, but it has a lot of resource hydrocarbon in place. And this is, we'll talk a little bit later. The way to produce this is by making permeability in order to produce it by the famous process called fracking. Now, in a conventional reservoir, what three conditions do we want to occur in order to have reservoir volume for an oil or gas volume of sufficient economic quantities? Three things need to occur. First, there needs to be a source rock where it gets generated, the hydrocarbon gets generated over millions and millions of years of pressure and high pressure and high temperature. Then the hydrocarbon, which is called in the layer called the kitchen, gets cooked. And then for that hydrocarbon to migrate from the kitchen, it needs a porous, permeable medium, a rock that will allow it to flow. And finally, the last part of the process is the entrapment. Basically, there has to be a way of blocking that migration of hydrocarbon that being gas or oil, so that it can accumulate in a sufficient quantity, sufficient economic quantity to be able to be produced. Now, we could have other conditions like this generation, but there's a really tight rock above the generation source that basically will not happen. Or that's what we call unconventional shale reservoirs. You know, we could have migration after the generation, but no entrapment, which means that over millions and millions of years, the hydrocarbon would just get lost. So very important to know, we need generation, permeable rock that will allow the hydrocarbon to migrate, and a way of entrapment of that volume. A couple of concepts. The first one is porosity. So what's really porosity? It's the void space in the reservoir rock in which you store fluid, could be including hydrocarbon, could be oil, could be gas, could be water. Okay, so if we look at microscopically the grains of sand, you can see the dark spaces. That's the porosity, that's the void space. Okay, and that really is what determines how much volume of oil or gas it's stored in a reservoir. The theoretical porosity, if all the sand grains were perfect spheres, it would be 33.3%. But as we know, we have different types of reservoirs, different types of porosities, like fracture porosity, that essentially allow higher volumes to be stored. Again, this is the porosity, this is the void space which allows hydrocarbon to be stored. The second concept is permeability. And essentially what is permeability is the ability to flow from a reservoir. So in the case of the porosity, we talked about it's the void space. But permeability is really how well connected are these void spaces. You can have a lot of void space, but not very well connected, which means that it will not flow naturally. It will not flow easily. And that means the permeability is very low. And if the permeability is very low, it will take a larger number of wells to produce, or you will need some stimulation for it to happen, increasing the cost and potentially making a field uneconomic. So very important concepts for porosity and permeability, which is essentially the ability to flow. In this equation, you can see flow, permeability, area, pressure differential at the wellhead, distance from the well, and viscosity. So all these factors are what affect flow. In terms of the hydrocarbon reservoir fluids, we have 5, which we'll talk a little bit later: black oil, volatile oil, retrograde gas condensate, wet gas, and dry gas. That kind of goes from the more dense and black, as you can see there, to the lighter hydrocarbon or gas. Recovery mechanisms. Essentially, in a reservoir, we have 3 recovery mechanisms: primary, secondary, and enhanced oil recovery. In the primary one, what happens is the natural energy of the reservoir basically is what drives the production of the field. In secondary or supplemental recovery, we help the reservoir maintain its pressure. And because the longer the pressure is maintained, the more the field will continue to produce. And finally, tertiary or enhanced oil recovery, as it's also called, is basically further technologies like polymer, surfactant, steam, and other products that get injected in order to try to recover more production. As you can see in this plot, the primary recovery is basically the first one that gives some recovery. Then you, for example, in this case, use a water flood or water injection wells to produce even further. And then enhanced oil recovery. Enhanced oil recovery, normally the projects that need a bit more investment and long-term payback. Then examples of primary recovery, we have depletion drive, solution gas drive, gas cap drive, water drive. For example, gravity drive, capillary drive, and compaction drive, all natural occurring primary recovery mechanisms. In terms of secondary recovery, we have water injection, gas injection, and also gas recycling. Let's talk a little bit more about unconventional resources. We have many options. Let's start with the ones that we already talked about. Coal seam gas or coal bed methane, which is the gas that comes out of the coals. We have what we already spoke about, the shales. We also have shales that basically are famous in which we can frack to make permeability so it can flow. We have tar sands and oil shales, like for example in Canada. We have deep coals with unconventional gas. We have underground coal gasification processes in which you basically burn gas in coals and produce a synthetic diesel product. We have geothermal recovery, which is you inject water in a very deep well. The heat of the earth will turn that water into steam, and then you can use that steam to generate energy. And then finally, we also have gas hydrates, all unconventional resources, and on all basically available in different techniques around the world. Let's talk a little bit about reservoir engineering tools. We have mainly two now with the advances of computation. Reservoir simulation is really a lot simpler and a lot easier to do. Hold on a second. And also we have another technique called decline curve analysis. So let's talk about reservoir simulation. Essentially what you do is you bring all the reservoir properties, all the reservoir layers, stratigraphy, the reservoir structure and geometry, fluid properties, pressure conditions, saturations, well geometry, if we have any existing ones, and you put all that and you're trying to basically represent that into a mathematical model. What do we get with our simulation model? First, and after we calibrate, we will able to predict the future of the field without doing any additional wells or with additional wells. Also, this helps us identify what oil or gas may be bypassed, and therefore it helps us determine the optimum well locations for future wells to be drilled. Now, what is decline curve analysis? Decline curve analysis is basically a simple and quick analysis that allows you to determine the future production of a well based on historical performance. As you can see here is a simple log plot. You basically try to fit a line on the production, and with that trying to predict which way the production is going to go. And then at one point it may reach the economic limit. In an oil field, for your information, there's no rate by which you can determine that the field will be uneconomic. What I mean is there's other conditions like oil price, like operating costs, that really determine the economic limit, not the rate limit of a field. Okay, let's talk a little bit about wells. A well has a long variable life cycle, started from drilling of the well. It can be then stimulated. It can be flow back. A completion could be run. A connection could be done. A commissioning of facilities could be happening, and then we start operating. But that's not the end. You know, it will need some maintenance, some enhancement in terms of workovers to keep the production going or to enhance it. And then finally, it will reach its stage of abandonment. So those are basically all the different phases that a well can go through. In terms of petroleum wells, well, what is a well? It's basically the general term for any bore through the earth designed to acquire hydrocarbons. So in terms of wells, we have different types, but essentially it's the same well. Wildcat, if it's in an area that there has never been any known oil or gas production. Appraisal wells, when you're trying to determine the productivity of an area. Exploration wells, where you're trying to simply find or confirm information on areas. And then we go into producing wells, in which we can have oil producers, gas producers, water injectors for pressure maintenance, aquifer producers if we need to get some source of water for water injection, for example, and also gas injectors. Those are all the different oil and gas and water producing wells types. Rig types. So what do we have? For drilling rigs, we have onshore rigs, we have platforms from where drilling occurs. We have mobile offshore drilling units, such as jackups for waters up to a depth of 100 meters. Semi-subs and drill ships, we can take us basically to further depth. But those are different types of rigs. Now, in terms of rig components, the main components are four. We need a power system to be able to give energy to all the system. We need a hoisting system to lift all the equipment that needs to go down in the well. We need a rotating system, which basically helps the drilling process through the bit. And we need also a circulating system, which will help us recover the drill cuttings as we go down into the reservoir. Okay, we will now talk about how well is drilled and constructed. Okay, so we have here our presentation of the surface by a bird and a tree. We have a first layer, which could be an aquifer. And we have now an intermediate layer, which is basically trapping the hydrocarbons, and the hydrocarbon layer is the one that we're trying to reach. So we get a drilling bit and we start the process of drilling a well. So what's happening as we start making hole in this well? Well, there's an equation that you probably know, which is pressure is equal to density, gravity, and height. So essentially, as we drill the well, we have two pressures that we observe. One pressure is on the well and the other pressure is on the reservoir. So the pressure of the formation is P2, and P1 is the well pressure, which will be the density of the fluid that you're using to drill, the gravity, which as we know is constant, and H is the depth. So the idea is to keep, as we drill through, a balance between these two pressures so that the following conditions occur and can be prevented. If the pressure of the well is higher than the pressure of the formation, what's going to happen is that fluid from the drilling of the well will go into the formation. If the pressure of the well is less than the pressure of the formation, then what we'll have is formation fluid, in this case water from the aquifer, will go into the well, and we don't want that. So the idea is to keep both formation and well pressures at an equilibrium as we continue to drill. So in this case, we continue to drill and we reach the bottom of the first layer. Now, because the pressures on this layer are different to the pressures on that layer, we want to secure this phase of the drilling. And what we do is that we run a metal pipe called casing in order to isolate this area before we can continue to drill into a different type of formation and different pressures. So what we do is we run the casing, which is basically a pipe. We run a set of plugs with cement in between. We apply pressure into the upper plug, and then basically at a rated pressure, the center of this plug will break and allow the cement to be distributed evenly all around the casing. And following some pressure tests and logs, we confirm that the cement is well around the casing, giving us a good bond between the casing and the formation. and therefore we will not have any leaks, we will not have any problems, and then we're able to continue to drill to the next layer. So we go to the next layer, same process, we have two pressures, we keep at equilibrium, we reach to the bottom, and before we enter the hydrocarbon zone, we run a smaller diameter casing, smaller plugs, cement, volume, and another plug. We apply pressure again, and that way we basically are able to fill the annulus space of between the casing and the other casing. And then finally, to reach the reservoir, we drill again. So what you can see here is a well constructed with integrity. There are two types of integrity. There's the geological integrity that it's already happened from the fact that you have a formation that has trapped the hydrocarbons and is preventing any leakage into the aquifers. But also, as we have now put a hole through it, we want to make sure that there is well integrity, and the well integrity happens from a well-constructed well with good casing and good cement bond between the layers. Having this integrity is very important for the entire life of a well to make sure that it doesn't have any problems. You don't have to be an engineer to know that if there's any problems in this integrity of the cement, for example, is that that the hydrocarbons are gonna try to find the easiest path of flow, which could not necessarily be through the well bore, but actually behind the casing. So to avoid that, we basically ensure that the cement jobs and the casing jobs are done correctly. Directional drilling basically is just a concept to confirm that depending on the location of the drilling rigs and depending on the objective or the target reservoir, we may need to do some extended deviated wells, S-shaped wells if they're coming from a formation, or J-shape if you want to do some reaching away from a platform. Okay, now we'll talk about logging. Logging tools that can be used to measure and determine the formation density, porosity, permeability, type of layer, which way the natural fractures orientation is going, pressure, oil, gas, and water content, and temperature. And then this is more than just squiggly lines. What happens with this well logging, which is part of three types: the geological logs, mud logs, and geophysical, and petrophysical logs, is what helps us determine where is the oil, where is the water, and what we can do. The process is very simple. You drill the well, you lower a tool to the bottom of the well, and you basically pick it up slowly. And as you pick it up slowly, you're reading the different layers and hydrocarbon contents of a well. Now let's talk a little bit about well completions, artificial lifts, and workovers. In terms of completion types, we have an open hole completion where the formation is basically strong enough so it will not collapse, and therefore we're able to produce the well without any issues. However, if we have a formation that is unconsolidated, then we need a way of minimize the solids from the layer to come into the well and potentially block it. And that's why we sometimes run what we call slotted liners. Now, if the sand formation is very important, then we need to run a process called gravel pack, which essentially is running a screen with a sand of engineered this size, which basically help us produce the fluids without keeping any formation solids from coming into the well. Finally, conventional on probably one of the most popular are you cement all the intervals and then you do what you call a perforation, which basically you get holes, you create holes through the casing, through the cement into the formation in order to produce the fluids. And finally, you may want to also have other options such as a perforated cemented liner, in which a cemented casing, sorry, in which basically the casing has gone through, and you basically already decided that the casing will have a screen from which you can produce. So these are the different completion types. Artificial lift. What happens here? Well, basically any system that adds energy to the fluid column in order to produce. This normally happens when the energy of the well, of the reservoir is not, doesn't last long enough, and we need to help it. So we need to have different types of artificial lift. The most popular ones are gas lift, PCPs, ESPs, and beam pumps. But we also have other ones such as plunger lift, hydraulic pumps, and jet pumps. We'll talk about 2 or 3 of them at the moment. Beam pumps, which basically essentially uses a surface beam and a crank assembly to drive down a piston. Now what happens is this piston or cylindrical device goes down into the well, captures a section of oil and sometimes water, and then lifts the fluid to the surface. And by a continuous movement, it basically is providing help to the fluid in the well to be produced. Gas lift is, if you remember the equation of pressure, density, gravity, and height, what happens here is we have a situation in which the weight of the oil column gives pressure higher than the pressure on the reservoir. So what we do there is we try to minimize this pressure on the wellbore, and we do that by reducing the density. How do we reduce the density? By injecting gas. And this can be done by what we call gas lift valves, which basically help inject gas that comes down through the casing into the well, making the column of the oil lighter, and then being able to produce the well. And ESPs, or electronic submersible pumps, are basically a pump attached to an electric motor. We run it downhole, and then we give it energy so that the well can produce for a lot longer. You know, if we leave it to simply produce by its own, it will probably die very soon. This normally is used as well when we have, for example, the first stages of water production. As the water comes into the well, the weight of the column will be higher, and it will prevent us from producing substantially. This is where we run these ESPs, these pumps, to basically produce larger volume. Workovers. What is a workover? A workover is basically a repair or a stimulation of an existing production well for the purpose of restoring, prolonging, or enhancing the production of hydrocarbons. So we have different options that we can see here. We can kill, we can bullhead, we can swap, we can clean out, wash over, snubbing, fishing, etc. But essentially, for the purpose of production enhancement, we have three types. We have reperforation, acidization or acidizing, and hydraulic fracturing. And what this does is that these are activities that are done in order to enhance the production of a well. In terms of equipment and tools that we use, we have coiled tubing, which is essentially a very steel hose, a very long steel hose. It's normally about 2-inch diameter, which can be used to do pumping down a well, normally deviated well. This is not used really for a vertical well. We have flashback units, which are small units that help us clean up the well. And rigs can be small for this in land, for example, right? A snubbing units, basically something that allows us to recomplete the well, running hole, or pull out existing completions without the need of having the well in a killed status. It basically allows you to work on a live well. And for that, you need basically a set of a set of slips that basically come in with a snubbing unit. All right, production process. So, or processing, sorry, what do we call that? Okay, so here's an example of process plant. Just to clarify, this is not a refinery yet, This is the first stage of processing in an oil and gas field. So we have from the subsurface through the wellhead, we have oil, gas, and water, and that it will go into a separator. Now, because of gravity, the gas will go out from the top, water from the bottom, and oil from somewhere halfway. But not all the gas that comes out will be dry. It will have a bit of oil and it will have a bit of water. So this is why the gas that comes out will go through the process of dehydration to remove the water, and then NGL extraction or condensate extraction that will come from fractioning units. It will also have some H2S and other contaminants removal. And then finally, the gas will be compressed for the purpose of selling. Now, the oil that comes out will have also a little bit of water and also a bit of gas. It's not perfect separation. So in terms of oil processing, we'll have a dehydration unit, we'll have a degassing or stabilization unit, and also contaminant removal. And finally, the water will come with a bit of oil and possibly with a bit of gas as well. So in terms of the oil, we'll have the oiling treatment water processing facilities, which will then help us, if we have clean water, to use it for other options such as irrigation, dust suppression, environmental schemes, or to recharge an aquifer. No, we can also use the water for secondary recovery, for disposal, and the gas that comes out, we can also use it for gas lift, as we mentioned before, or for enhanced recovery. So as you can see, this is what happens in the first stage of processing in a gas plant. But I reiterate, this is not a refinery. This is just the first stage that help us separate the products, remove the contaminants, remove oil or water from the gas before it can be sold, and likewise remove any gas or water from the oil so it can be sold. Gas compression, essentially what we're trying to do in a gas compression is we try to raise the pressure for transportation or to meet the requirements of the facility specification. We have different types of compressors. We have screw compressors for smaller volumes, and we have centrifugal compressors for larger volumes. But the idea is to raise the pressure in this example from 70 kPa all the way to 11,000 kPa, which is normally the required pressures for gas pipelines. Water, what happens with the water? Well, it's still in some countries allowed is they use the evaporation ponds when the volumes are not significant, or for beneficial use, which is more of the case these days. It can be used after cleaning for irrigation, for industrial uses, for dust suppression, for local irrigations. It can be reinjected, as we mentioned before, into secondary recovery mechanisms, and the idea is to also have environmental surface discharges. Gathering systems, something very forgotten, which is really the flow lines that connect the wells to the facilities, compressor stations, etc. So as you can see, we have different types. Really, they really depend on the field development plan, the topography of the terrain, and other considerations. So we can have central systems, axial systems, branch systems, and loop systems. Transport and storage. Okay, we can have a national gas distribution pipeline. We have gas transmission pipelines. In terms of NGL, we can store that and transport it in pressure tanks. We can combine it with liquid streams. It can be trucked in the road and also in trains. Crude oil, it can go through temporary storage tanks, pipelines, railroads, and also offshore oil tankers. Okay, now let's talk about a little bit about the downstream processing and facilities. In terms of downstream operations, we have the gas processing and the petroleum refining. In terms of gas processing, from natural gas, we can get LNG and gas to liquids, which basically give us final products of methane and LPG. And then we have the petrochemical industry, because from all that gas we can get plastics, and obviously some of the stuff from the oil, plastics, synthetic fibers, fertilizers, lubricants, healthcare products, etc. From the crude oil, the distillation process allows us to get naphthas, gasoline, jet fuels, kerosene, diesel, and other heavy products that also go into the same petrochemical industry. What's an LNG chain? Well, in terms of LNG, what we're trying to do here is to transport the gas, but the way to do it is we basically put it through a process of freezing it in an LNG plant and turning that into a liquid. Once it's a liquid, basically it's very stable. It can be put on LNG tankers, and then it can be sent to what we call receiving terminals, where the liquid gas is heated up again and regasified, and then it can be used again as gas for the power generation unit or any distribution that may be required. Crude oil refineries, how do the refinery works? Essentially, the process is very simple. We get the crude oil to go through a furnace, and then initially on a tall tower, the temperature at the bottom is close to 400 degrees centigrade. And as it goes up in the column, it starts changing its temperature profile. And depending on the different types of or different levels of temperature, then we can extract the different products. In this example, gasoline from 150 degrees, kerosene from 200 degrees, diesel from 300 degrees, etc., etc. And any heavy ends will basically become asphalt. So that's essentially what happens in a refinery. You know, you heat it up, you go put it through a tower, and as it goes up and cools down, you're able to extract different products. Finally, petroleum consumers, we have power generation, aviation, transportation, and also obviously the manufacturing industry. Our last slide is just a reminder, the use of petroleum, obviously for vehicles, jet fuel, cooking and heating gas, fabrics, fertilizers, house chemicals, plastic products, electronics, drugs, and cosmetic products, and inks, dyes. Very much everything that we can think of and more basically comes from oil. Well, thank you very much, Victor. I have finished the presentation. Should there be any questions, please?
Okay, Mr. Jorge. Yes, thanks for sharing your information of experience, you know, and knowledge. If anyone has any question, you can raise your hand or write in the chat now, no?
Okay, I can see a question. Would you like to remind us the parameters to evaluate injection gas lift? Okay, so the first thing about gas lift is you need to make sure that you have enough gas in your production so that you can have a sustainable gas lift system. Okay, I have worked in reservoirs that it sounds like a good idea to have gas lift, but we did not have enough or sufficient gas in the field. So we could not consider gas lift, and we had to use other method of artificial lift, in this case, electrical submersible pumps. So the first thing is availability of gas. Then is the distribution. How can you get the gas to to be connected into your wellheads? And also, and most importantly, one of the important parameters is the conditioning of the gas. We cannot, unfortunately, just inject the gas as it comes from the ground. We need to condition it, we need to dehydrate it, so otherwise we're going to have problems as we inject that gas down the casing for gas lift. So 3 considerations. One more time, the availability of gas for the duration of the life of the field, the distribution of it, because you will need compressors and etc. to raise the pressure of the gas. And thirdly, the conditioning of the gas. I think those 3 parameters cause of making the use of gas lift uneconomic or simply not feasible in a reservoir. Okay, what difficulties in the well has been the most frequent? Integrity. When this comes from 2 aspects. The well probably was not drilled properly at the beginning. It had some issues reflected by some pressures on the annulus of the casing, which normally should be 0, to be more than that, and that already is telling you there's a problem. But also during the life of the well, we do not do proper maintenance because of cut cost or whatever other reasons. And we basically, we don't watch the type of fluids that are coming from the well, and we end up having some corrosion problems or flow assurance problems, which also basically minimize our ability to produce, because it reduces the flow or because it creates a well that is not basically able to produce because it simply doesn't have integrity. So integrity and flow assurance. Okay, what methods for the development of the areas on the northwestern of Peru without drilling new wells? Well, the reservoirs, as I understand it, in north of Peru, are very compartmentalized, unfortunately, which means that they access only small pockets. Unfortunately, the only thing that we can do there is a continuous stimulation by fracking. It's basically trying to reach as much as possible all areas of the compartment of reservoir in order to produce. Okay, question, how many years do you think we can use this type of energy? Well, as an energy, we all know that the next transition comes from oil into gas. So really we need to focus more on the gas side, as it's a cleaner fuel, as a cleaner resource, okay? But we'll still need some oil for basically all the other products that we need to produce. How long? Really, as always, unfortunately, it's not a question of stopping the source, but it's a question of stopping the demand. If there continues to be demand for energy, well, oil will be here for a long time. I come from a 2nd generation of family of petroleum engineers, and at the time that we were at university, they tell us the oil is going to run out, that this is the end, and it continues and continues. So without predicting the future, this oil industry is here to stay for some time now. Okay. Any other questions? What do you think about the dual application completion? Dual completion for wells in the north. Okay, dual completions are very good because they allow us to produce separate zones at different pressures or different reservoir fluids, allow us to inject on one side and produce on the other zone. The only thing that we need to be careful about is obviously the cost and in the deployment. Remember that you're trying to put not one now, but two very small pieces of pipe into a small hole, 8 inches, 10 inches. I don't think so, more like 8 inches. So these are very tight, very small tolerance wells. So there's complexity. And unfortunately, with complexity come the costs of installing and also the cost of maintaining, especially when something goes wrong. So sounds like a good idea, but we need to evaluate the risks and the costs associated with that. Any other questions? Okay, Victor, I think that's the end of the presentation, the end of the questions.